Hello there and welcome to another one of my videos. This one is on finding the arc length of polar curves. So let's get started. Find the arc length of the entire perimeter of the region inside r equals 12 sine theta, but outside r equals 4. So we know from watching one of my previous videos that r equals 12 sine theta is a circle. And r equals 4 is also a circle. So if we were to go to Desmos and draw these, we have the big red circle, which is r equals 12 sine of theta. And we have the smaller blue circle, which is r equals 4. So let's just draw a quick little sketch of what this is going to look like. So we have our bigger circle here, and we have a smaller circle centered at the origin here. All right, now what is not completely obvious from the actual wording of the problem is what it is that we are looking for here. So what we are looking for here is this area, this arc length here of the larger circle up until we get to the smaller circle. It says it does not want the arc length of the area that's inside r equals 4, but rather outside r equals 4. So what we have to do is find this arc length right here. Okay. So we're finding the larger arc length of the bigger red circle, and then we are finding the arc length of the smaller circle here. So on my diagram, I'll just that's going to be all of this area in here. And then in through here. So essentially what we have to do is we have to find two different arc lengths. But a key to being able to do this is to find where these two curves cross. We need to find that point there, and we need to find that point there. So the easiest way to do that is to find where the two curves intersect. So if we take 12 sine of theta and set it equal to 4. In other words, we're taking the two curves, we're setting them equal to each other. Or the sine of theta is equal to 4 over 12, or 1/3. Well, if the sine of theta is equal to 1/3, then theta is going to be equal to the arc sine of 1/3. Well, I don't happen to know what that is offhand. And that's going to give me this point right over here. Then we have to find this point right over here, which we're going to find by, so this would be theta 1, and theta 2 is simply going to be pi minus the arc sine of 1/3. And so I'm going to use Desmos to calculate these. And using Desmos, I did that over here. We have the arc sine of 1/3 is 0.3398. And then pi minus the arc sine of 1/3 is 2.801. So those are going to be our bounds of integration. Now here's a really nifty thing. Just to confirm that these are the points of intersection, what I like to do is go up here to my polar curve, r equals 12 sine of theta, and put these numbers in. So the larger number is going to be 2.801, 2.801, and the lower 2.8, let's do that, 2.801, and the lower one is 0.3398. And notice that, yeah, that's the curve starts here and ends right there. So those are they appear to be pretty darn close, at least, to the bounds of integration that we're looking for. So let's go back to our problem here. And so our upper bound of integration is 2.801. And our lower bound is 0.3398. All right, so our formula for finding arc length is, so I'm going to say L1 because we have two arc lengths to find. L1 is going to be the integral from alpha to beta of the square root of the function squared, f of theta squared, plus f prime of theta squared d theta. And so that's the general arc length formula that we're going to be using. And so for L1, we know that that's going to be from 0.3398 to 2.801. And then we have the square root of the function squared. The function is 12 sine theta. We want to square that. And now the derivative, so we have r is equal to 12 sine theta, and so r prime is equal to 12 cosine theta. 12 cosine theta squared d theta. Well, we can do all kinds of nifty things with this. First of all, we can, underneath the radical, we can factor out a 144 because 12 squared is going to be 144, and 12 squared here, 144. We can factor that out. And then we're going to have a sine squared theta plus a cosine squared theta, d theta. And I know you are already seeing what's going to happen here from 0.3398 and 2.801. Oh, L1. Sine squared theta plus cosine squared theta is equal to 1. 1 times 144 is 144. The square root of 144 is 12. Well, how nice. We seldomly ever have radicals that work out that nicely. So we end up with simply 12 d theta. And when we evaluate that, so what are we going to do to evaluate this? Well, we're going to add the integral is then going to become 12 theta from 2.801, 0.333 or 3398. There we go. And so that is going to end up being equal to 29.534. So that's L1. Now L2 is going to be even easier than that. L2, so we're going to have the same bounds of integration, 0.3398 and 2.801 of the square root of my function 4 squared plus the derivative of 4, which is 0 squared d theta. So 4 squared is 16. Square root of 16 is 4. So L2 is simply the integral from 0.3398 to 2.801 of 4 d theta. Well, integrating that, we get 4 theta from 0.3398 and 2.801, and that ends up being equal to 9.848. So our final answer then, of course, the entire arc length is going to be the sum of L1 plus L2, which was going to be the sum of 29.534 plus 9.848, which will end up being 39.3792. And so that is the total arc length. So once again, L1, let's go back to our Desmos graph. L1 is the red arc length. That's what we did when we calculated L1. L2 is the arc length of the smaller blue circle between the bounds of integration right in here. So we added L1 plus L2 to get the entire arc length. All right, so that's the video. I hope you enjoyed it, and I hope it was helpful. See you in the next one.